There are billions of habitable planets in our galaxy alone.
The James Webb Space Telescope is shaping up to be one of the most significant breakthroughs for humankind regarding space observation. Being far more powerful than all other space telescopes ever launched by humans, the scientific community has high hopes. Stars may be billions of miles away from us, but they are very fascinating objects. While many people simply adore how they light up the night sky, scientists are especially interested in the planets that orbit them. And scientists now have more reasons than ever to pay attention to one of these planets, as the new powerful James Webb Space Telescope has just discovered signs of life on it. What signs did the JWST discover? Which planet has the telescope made this discovery on? What does the discovery mean for deep space exploration? Stay tuned as we bring you how the James Webb Space Telescope has just discovered signs of life on Proxima b. Space exploration is a very expensive endeavor. However, when NASA set out to develop the most powerful space telescope ever, the agency had no idea it would cost so much in time and money. The James Webb Space Telescope, the new darling of the space scientist community globally, would cost NASA and its collaborators $10 billion and decades in design, construction, and testing. And the cost and time were far from the only problems with the JWST as far as NASA was concerned. The whole world held its breath on Christmas Day of 2021 when the telescope launched into space. Right in that contraption were 344 single points of failure, enough to wreck the nerve of even the most seasoned engineers. Everything about the JWST is complex. It has an origami-like structure, and over the course of its ascent to its permanent location in L2, which took a month, the 18 honeycomb-shaped cryogenic mirrors of its upper section had to unfold and fan out to form a large mirror with a final size of 6.5 meters. Each of the 18 hexagonal mirror pieces of the upper section had to align within 1/5000th the width of a human hair. That is basically no room for error. Even the operating temperature can be a problem for the JWST, as it requires extreme, unimaginable temperatures. The upper, sun-facing portion has to remain consistently at 85 degrees Celsius, but the other side must be maintained at approximately minus 233 degrees Celsius. To maintain such homeostasis, the two sections are separated by a precisely positioned 5-layered sunshield, each successive layer cooling the space beneath. If the temperature is not kept so low, there will be infrared background noise. To achieve this extraordinary cooling requirement, the JWST had to utilize the world's coolest element, helium, for the mid-infrared instrument's cryocooler, or a refrigerator designed to reach cryogenic temperatures. The technology surrounding the mid-infrared instrument, or MIRI, marked a huge stepping stone in the field of astronomy. The longer the wavelength of infrared, the cooler the detector needs to be. Given the ambitious 14 billion-year observational path of the JWST, its detector system has to stay at less than 7 Kelvin to operate efficiently, minus 266 degrees Celsius. Understandably, the scientific community expects big things from the JWST. With the launch and configuration now gone smoothly, the Space Telescope will support about 300 observation programs during its lifetime. But what exactly is NASA planning to do with its $10 billion space telescope? The JWST is not the first iconic space telescope launched by NASA. It was preceded by the Hubble, which deserves lots of credit for unlocking new levels of deep space study. However, as powerful and versatile as Hubble is, it has some limitations. For example, it can't detect the first galaxies. However, the JWST is optimized with unparalleled infrared technology to detect faint infrared light from 14 billion years in the past, looking at a part of space that we have never seen before. As claimed by NASA, this massive observatory will be able to see the light of a bumblebee at the distance of the Moon. Compared to its predecessor, the JWST has a 15 times wider field of view on its main camera and collects 6 times the light. meaning for the first time we will be closer to establishing the makeup of the unique origins of the universe. In order to make these discoveries, the JWST's camera will be trained deeply into one patch of sky for extended periods of time to gather as much light and information as possible. The JWST will also help us understand dark matter and dark energy. These two concepts are among the most mysterious in the entire universe. The new telescope will take images to observe disturbances in what is known as gravitational lensing. In other words, these images will seek to make the invisible visible. Have you ever seen a funhouse mirror before? Well, space and time can be curved or warped in the same way. You might be surprised by this, but gravity bends the path of light. So when light travels through space-time, it can dip and curve in the presence of large objects. This process of distortion is called gravitational lensing. The JWST will investigate the nature of gravitational lensing patterns from distant galaxies, further expanding what we know of both the structure and expansion of the universe. One major theory concerning the nature of dark matter's role in the Big Bang comes from Hawking's primordial black holes theory, the idea that dense regions that existed in the hot and hyper-compact early universe became the first black holes. However, it may go either way, as the JWST may serve to prove or completely debunk this idea, but it can potentially serve up competing alternatives. For instance, the theory about black holes resulting from the collapse of stars, so it is an exciting time to be alive. Many astronomy experts are keen to see whether or not black holes existed since the beginning of time, or whether they came to fruition only after the first generation of stars died out. If the JWST manages to detect the first light of the universe, and thus the stars which formed mere moments after the Big Bang, this question may be answered at last. One other important thing that the JWST will help scientists with is the study of exoplanets, and one of them, Proxima b, is particularly exciting because of the huge potential that it has. Basic geography says all of the planets in our solar system orbit around the Sun. However, there are other planets that orbit around other stars and are called exoplanets. The problem with exoplanets is that they are very hard to see directly with the telescopes. They are obscured by the bright glare of the very stars they orbit. So astronomers use other ways to detect and study these distant planets. They search for exoplanets by looking at the effects these planets have on the stars they orbit. However, before the JWST, scientists were using a number of methods to detect exoplanets. One way is to look for wobbly stars. A star that has planets doesn't orbit perfectly around its center. From far away, this off-center orbit makes the star look like it's wobbling. Scientists have used this method to discover hundreds of exoplanets. However, only big planets as big as Jupiter or even larger can be seen this way. Smaller Earth-like planets are much harder to find because they create only small wobbles that are hard to detect. NASA even launched a spacecraft called Kepler to look for exoplanets. Kepler looked for planets in a wide range of sizes and orbits, and these planets orbited around stars that varied in size and temperature. And some of these planets discovered by Kepler are rocky planets that are at a very special distance from their star. This sweet spot is called the habitable zone, where life might be possible. Kepler used a method known as the transit method, which works like this. When a planet passes in front of its star, that is known as a transit. As the planet transits in front of the star, it blocks out a little bit of the star's light. That means that naturally a star will look a little less bright when the planet passes in front of it. Astronomers can track how the brightness of the star changes during a transit. This can help them figure out the size of the planet. Using the transit time, astronomers can work out how far away an exoplanet is from its star. But it goes more than that, as the information can tell us about the planet's temperature. If a planet is just the right temperature, it could contain liquid water, an important ingredient for life. So far, the Kepler mission has been more successful than the wobble method, as it has discovered thousands of exoplanets. But how will the JWST discover exoplanets like Proxima b? Well, we're in for a treat, as the JWST will be able to study the atmosphere of exoplanets. When a transit is detected at several wavelengths, it can help to measure the atmospheric composition of the exoplanet. For example, water molecules strongly absorb light in the infrared wavelengths, making the planet appear larger since its atmosphere blocks a larger fraction of the light from its star. Using a similar method, it's also possible to measure the temperature of the atmosphere and to detect the presence of clouds. Now, we have talked about a planet passing in front of its star relative to us on Earth, but a transiting planet can also pass behind its star. This phenomenon, in which only the light from the star is observed, is called a secondary eclipse. By observing this, it's possible to isolate the light coming only from the planet and thus obtain additional information about its atmosphere. Generally, the transit method is more sensitive to the presence of clouds, but the secondary eclipse method provides more information about the temperature of the atmosphere. When scientists study an exoplanet's atmosphere, they use the one-dimensional approach. This means the composition and temperature are taken to vary only with altitude. They don't consider its position in longitude and latitude. Taking these three dimensions into account simultaneously would require complex models as well as a high degree of observational accuracy. However, solely considering altitude may produce approximations that are not valid. On Earth, for example, the temperature at the equator is much higher than that at the poles. Some exoplanets also have strong spatial variation in their atmospheres. Hot Jupiters, or exoplanets similar in size to Jupiter, orbit very close to their host star and can thus reach temperatures of several thousand degrees Celsius. There is something else about the movement of these exoplanets. They generally revolve around themselves at the same speed as they do around their star. The implication of this is that on these planets, a day and a year are the same lengths. And don't worry, we are going somewhere with this. In the same way that we can only see one side of the moon from Earth, only one side of a hot Jupiter constantly faces its star. This phenomenon can lead to a large temperature difference between the day side, which is illuminated by the star, and the night side, which is perpetually in darkness. It is basically impossible to an exoplanet's surface directly, but using the spatial variation of the atmosphere. This involves two methods: phase curve analysis and secondary eclipse mapping. The phase curve is the variation of light from the star-planet system during a period of revolution. Knowing the planet rotates on itself during its orbit, scientists watch out for different sections of its atmosphere as they become successively visible to us. Using this signal, you can map the intensity of the light emitted by the planet in longitude. In the case of hot Jupiters, with the day side generally hotter, the maximum of light from the planet is near the secondary eclipse. Similarly, the minimum of the curve is near the transit, since it is then the night side that is observed. In secondary eclipse mapping, the day side of the exoplanet is resolved. As the planet moves in and out from behind its star, from our point of view, sections of it are hidden, allowing us to isolate the light emitted by a given section of its atmosphere. By measuring the amount of light emitted by each individual section, it is then possible to map the day side of the atmosphere against longitude and latitude. And with its 6.5-meter mirror, the JWST can produce unprecedentedly precise observations over a wide range of wavelengths. It is equipped with 4 instruments, including Canada's near-infrared imager and slitless spectrograph, and can observe in the infrared range and characterize the atmospheres of a multitude of exoplanets. With the JWST, scientists will be able to apply multiple mapping methods to measure the 3-dimensional variation of exoplanet atmospheres. These measurements will allow us to deepen our knowledge of atmospheric processes. Its first exoplanet. The photo shows the bright blob of a planet that is 7 times heavier than Jupiter, orbiting a star nearly 400 light-years away, even further than Proxima b. The groundbreaking result is the latest in a slew of early exoplanet findings from the telescope and a test of technologies that will enable direct imaging of Earth-like planets by future space telescopes. The image was produced by a team of astrophysicists led by Sasha Hinckley, the University of Exeter in the UK. The team pointed the JWST at the fast-spinning star HIP 65426, where a planet was already known to exist. The Sphere instrument on the Very Large Telescope in Chile first photographed the planet in 2017. Hinckley's team was trying to test and characterize JWST's ability to see the planet, called HIP 65426b. It is interesting how the JWST photographed HIP 65426b. the telescope blocked the light of its host star using a small mask called a coronagraph. This showed up the orbiting planet, which is thousands of times fainter, like detecting a firefly around a searchlight. HIP 65426b orbits about 100 times further from its star than Earth does the Sun. It takes 630 years to complete an orbit. This distance makes it easier to see the planet against the glare of the star. And that, coupled with the planet's extreme heat and thus brightness, it has a scorching temperature of about 900 degrees Celsius, a fever left over from its formation just 14 million years ago, makes it a prime target for direct imaging. Showcasing the potential of the JWST in studying Proxima b, the telescope's size and sensitivity allowed it to collect more light from this planet than any previous observatory has obtained. With this, Hinckley and her team were able to get a better estimate of HIP 65426b's mass, which they calculated to be about the size of 7 Jupiters. They were also able to calculate the exoplanet's radius at 1.4 times that of Jupiter. The giant planet is far from hospitable to life as we know it, but it is a class of large planets that scientists are eager to learn more about. Jupiter probably played a key role in sculpting our solar system, perhaps enabling life on Earth to take hold. But of course, an exoplanet does not have to be the size of HIP 65426b to be visible to the JWST. Thanks to its exceptional stability, the telescope can study exoplanets the size of Neptune and Uranus. Proxima b is especially fascinating to scientists. For several reasons, it may be the first planet where we will discover extraterrestrial life. This alien planet orbits the closest star to us, Proxima Centauri, is slightly larger than the Earth. Proxima b's parent star, Proxima Centauri, may be the closest to the Earth, but it's part of an odd stellar trio that astronomers still don't quite understand. The other two stars are binary, meaning that they orbit a common center of gravity. Together, they're called Alpha Centauri. Astronomers aren't really sure whether Proxima Centauri is gravitationally bound to the other pair in some type of orbit or if it's just passing by. If it is bound, it would take 500,000 years to revolve around Alpha Centauri. If not, it will take millions of years to leave the area. You can easily see Alpha Centauri without a telescope. The binary stars combine to make the third brightest star in the sky. Although Proxima is slightly closer to Earth than its binary, it is also much smaller and dimmer than the other two stars. That's because Proxima is a red dwarf, and so Proxima Centauri is too faint to see with the unaided eye. Proxima Centauri is quite a tiny star. It is just over 1/10 the size of our Sun. However, if you were looking up to the sky from Proxima b, the red dwarf would look about 3 times larger than the Sun would look to someone on Earth. That's because of Proxima b's small orbit. The planet orbits its parent star at a distance of 4.6 million miles or 7.5 million kilometers, which is only 5% of the distance between Earth and the Sun, which is 93 million miles or about 150 million kilometers. And while our Sun is a bright, massive star in Proxima b's sky, people on Earth need special equipment to be able to see Proxima Centauri. Proxima Centauri b does not orbit its star in front of us. That is to say, if you were to look at Proxima Centauri head-on, you would be unable to see Proxima Centauri b, as it does not cross its star from our point of view from the Earth. This makes predicting its orbit difficult. Astronomers don't know whether or not Proxima Centauri b has a nearly circular orbit or a highly elliptical one. Proxima b was detected by the effort of Dr. Anglada Escudé of Queen Mary University using the Doppler effect method. He developed a new method, Template Enhanced Radial Velocity Reanalysis Application, or TERRA. This method has been used to analyze data from the world's most precise radial velocity instrument, the European Southern Observatory's High Accuracy Radial Velocity Planet Searcher, or HARPS, via the HARPS TERRA software tool. So why do astronomers think there is a chance of life surviving on Proxima b? To start with, its minimum mass is 1.3 times the mass of Earth. This suggests that it's likely to be a rocky, terrestrial planet like Earth. It is even in Proxima Centauri's habitable zone, where temperatures are perfect for liquid water to exist. Apart from that, Proxima b remains the closest Earth-like exoplanet anyone has ever found, and at just over 4 light-years away. but that does not mean we can go there anytime soon or ever. Even with the latest technology, it would still take thousands of years to reach our closest neighboring star. Visiting Proxima b is out of the question for now. In April of 2019, a radio signal was detected and believed to have originated from the region of Proxima Centauri. The signal, which has since been named Breakthrough Listen Candidate 1 or BLC-1, was detected as a result of the Breakthrough Listen Project, which is an initiative set up to search for intelligent extraterrestrial communication throughout the universe. The project has received over $100 million in funding and has dedicated thousands of hours of telescope watch time in state-of-the-art facilities across the planet. Beginning in January 2016, the program still remains the most comprehensive search for extraterrestrial communication outside of our solar system. The signal or techno-signature was picked up by the CSIRO Parkes Radio Telescope in New South Wales, Australia. At the time of the discovery, the telescope was observing the region of the closest star to our Sun, Proxima Centauri, which it had done hundreds of times before. Over time, the telescope picked up vast amounts of data, and scientists didn't pick up the signal right away. At the end of each observation cycle, they had to filter through hundreds of thousands, sometimes millions of signals to single out any unique techno-signals which might originate from space. And to give you a sense of what they are looking for, the signals must have two distinct properties. The first was that it must be confined to a very narrow broad band of frequencies, much similar to radio broadcast on Earth. This is unique because no natural process is able to produce this kind of signal, and it will definitely raise red flags if it were to originate from space. The second property is that the frequency of the signal must drift in a way that is similar to the motion of exoplanets relative to Earth. During this particular observation cycle, the telescope in Australia picked up over 4 million distinct signals, and the team had to get to work filtering out unimportant signals and leaving out the rest. The team was able to filter out much of the background signals that originated from Earth and were left with over 5,000 distinct signals. The team then had to further cross-check these signals with radio transmitters currently on Earth and were finally left with a single, unexplained signal. The team of scientists described this signal as a unique techno-signature with a narrow broadband that appeared over a 30-hour observation period and only when the telescope was pointed towards Proxima Centauri. The discovery of BLC-1 indicated that it possibly originated from Proxima Centauri and had a distinct feature to the WOW signal discovered back in 1977. The WOW signal was a strong narrowband radio signal discovered by Ohio State's Big Ear Radio Telescope, which was the premier tool used in the search for extraterrestrial intelligence. The WOW signal appeared to have originated from the constellation Sagittarius and was the first sign of extraterrestrial communications outside our solar system. The signal lasted for about a 72-second window and has since not been detected by any other telescope anywhere else in the world. There have been several hypotheses to the origins of the WOW signal, including human-made sources, none of which have adequately explained the signal's origins. It currently remains the strongest possible evidence for a radio-transmitting extraterrestrial civilization outside the solar system. But what about gravity on Proxima b? Just like the Earth, this exoplanet produces gravity. Proxima is at least 1.3 times that of the Earth, and, well, could be much more. If Proxima b is spherical with a mass of, say, 1.5 Earth masses and about the same mass density as Earth, Proxima b's surface gravity would be about 1.145 g, or 11.22 meters per second squared. So you push the scale about 14% more than on Earth. But there is another variable that can change our calculation significantly. You see, the Earth has a relatively high density because of its iron-nickel core. However, Proxima b, like Mars, might not have such a core. So if, because of this, Proxima b has the same mass density as Mars, or 3.93 grams per cubic centimeter, Proxima b's surface gravity would then be 0.866 Gs, or 8.5 meters per second squared, and you would weigh 14% less than on Earth. But then Proxima b may not be spherical. The strong tidal forces would tend to give the tide-locked planet an ovoid or egg shape, with a long axis pointing at the star. So any habitable zone would be located in the mid-region of the ovoid, where its radius would be the smallest, meaning the habitable mid-region would be closer to the planet's center. Here, the surface gravity would be higher than in the hot and cold zones. If the radius was 10% smaller there, the gravity would be 20% larger. Proxima Centauri has frequent solar flares, and there is debate about whether the resulting ionization would strip away any atmosphere that Proxima b might have. It has been argued that if Proxima b has a molten core like the Earth and rotates on its axis every 11.2 days, this might be sufficient to generate a planetary magnetic field that would protect the atmosphere. Even if there is no native life on Proxima b, it may turn out to be an advantage. This is because many arbitrary branch points in the evolution of life could have resulted in life evolving on other planets very differently from what we have on Earth. This type of alien life would be very likely to be toxic to humans. So for a colony site, a sterile planet might be preferable to a biologically hostile one. Such pre-sterilization might make it easier to transplant some simplified version for Earth's ecosystem to Proxima b. What if aliens live on Proxima b? If that is the case, there is speculation that its improbable life could develop on the day side due to a constant stream of intense radiation from its host star. The reason is that Proxima b orbits just 4.5 million miles out, or about a tenth of the distance Mercury is from the Sun at its closest point. Radio signals have already been detected from the area around Proxima b. However, radio astronomers believe this was likely just interference from natural sources. So because the side of the exoplanet that is free from radiation is always dark, any civilization inhabiting the exoplanet may have to deploy powerful mirrors or acquire very bright LED-style lights to illuminate their cities. This can help us detect them using the right tool. This is why a team that includes Harvard astronomer Avi Loeb has suggested that the JWST can be configured to spot evidence of LED light on the planet Proxima b. They suggest that using the near-infrared instrument on the James Webb Telescope and looking for the telltale signs of LED light waves in the light from the planet and its host star, they will be able to detect this artificial light if it exists. The team has investigated whether artificial lights could be detected on the dark side of Proxima b by computing light curves from the planet and its host star. These scientists considered two different scenarios: artificial illumination with the same spectrum as commonly used LEDs on Earth, and a narrower spectrum that leads to the same proportion of light as the total artificial illumination on Earth. They discovered the JWST would be able to detect LED-type artificial lights, making up 5% of stellar power. If James Webb is able to detect the narrowband light that is reminiscent of LED bulbs, it will be because it will be able to characterize the atmosphere of the planet. This will allow researchers to use instruments on the observatory to detect how much energy transport occurs on the planet and then perform calculations of light curves to determine whether they match those of an LED light source or not. To come to the conclusion that it may be able to detect artificial light, Loeb and colleagues use the JWST Exposure Time Calculator. This tool allows astronomers to predict what can be detected in any given time period based on predefined settings before the observatory launches. It allowed them to determine the possibility of detecting different flux values and detecting those with a wavelength that matches artificial light levels that should be expected from a civilization forced to live in permanent darkness. In that case, the lights shining onto the permanent night side should be extremely powerful and thus more likely to be detected with JWST. The JWST will be able to show the existence of artificial illumination for standard LEDs 500 times more powerful than those currently found on Earth's, and for artificial illumination of similar magnitude to Earth's. In further research of the possibility of life on Proxima b, scientists have also tried to determine what the Earth as a planet would look like if it was orbiting Proxima Centauri. They relied on modeling to work out what the situation would look like. Again, we return to the concept of habitable zones. Just because Proxima b's orbit is in the habitable zone, which is the distance from its host star where water could pool on a planet's surface, doesn't mean it's livable. It doesn't take into account, for example, whether water actually exists on the planet or whether an atmosphere could survive in that orbit. Atmospheres are also essential for life as we know it because it allows for climate regulation, the maintenance of water-friendly surface pressure, shielding from hazardous space weather, and the housing of life's chemical building blocks. The scientists' computer model used Earth's atmosphere, magnetic field, and gravity as proxies for Proxima b's. They also calculated how much radiation Proxima Centauri produces on average based on NASA's Chandra X-ray Observatory observations. With these data, their model simulates how the host star's intense radiation and frequent flaring affect the exoplanet's atmosphere. An active red dwarf star like Proxima Centauri strips away the atmosphere when high-energy extreme ultraviolet radiation ionizes atmospheric gases, knocking off electrons and producing a swathe of electrically charged particles. In this process, the newly formed electrons gain enough energy that they can readily escape the planet's gravity and race out of the atmosphere. Opposite charges attract, so as more negatively charged electrons leave the atmosphere, they create a powerful charge separation that pulls positively charged ions along with them out into space. In Proxima Centauri's habitable zone, Proxima b encounters bouts of extreme ultraviolet radiation hundreds of times greater than Earth does from the Sun. That radiation generates enough energy to strip away not just the lightest molecules, hydrogen, but also, over time, heavier elements such as oxygen and nitrogen. The model shows Proxima Centauri's powerful radiation drains the Earth-like atmosphere as much as 10,000 times faster than what happens at Earth. Proxima b is tidally locked to Alpha Centauri. What does this mean, and what are the consequences? You probably know that the Sun and Moon exert tidal forces on the Earth's ocean. This type of force depends on the mass density of the producing object and on the power of the third object's angular size in the sky. Even though to an observer on the Earth, the Sun and Moon appear to have about the same angular size, the Moon's tidal influence is triple that of the Sun because the Moon has 3 times the Sun's mass density. Now, because Proxima b has such a small orbital radius, the star Proxima Centauri, even with its small diameter, will seem to have a 2.86 times larger angular diameter in the sky than does our own Sun, as viewed from the Earth. Proxima also has 40 times the density of the Sun. That means the tidal force of Proxima Centauri on Proxima b will be 939 times greater than that the Sun exerts on the Earth. So most likely, Proxima b remains tide-locked to Proxima Centauri. This means that, like Earth's moon, Proxima b would always present the same face to Proxima Centauri. The consequence is that Proxima b will have a desert-like hot side and a deep frozen cold side at the same time. But there will be a twilight zone band around its mid-region in which the star is always just above or just below the horizon. In this region, the temperature won't be extremely hot or cold. But then a tidally locked planet has its advantages. For example, if humans were to live there, it means solar energy farms would always generate electricity. The electricity will then be distributed to other parts of the exoplanet where it's needed. Colonists can just select a location with any average temperature they wanted and could hide from the periodic solar flares by keeping dangerous Proxima Centauri just over the horizon and out of harm's way. However, the colonists will have to cope with less sunlight. The light that your human eye can see, the visible spectrum, has a wavelength ranging from about 400 nanometers at the deep violet edge to 700 nanometers at the deep red edge. However, the sunlight from Proxima Centauri peaks at 950 nanometers, which is well into the infrared, and falls off rapidly in the visible region, with the visible light strongly skewed toward the red. So if light from the Sun and Proxima Centauri were equal at the red edge of the visible spectrum, the light from Proxima would be 10 times weaker at the violet edge. So don't expect to get a nice tan by lying on a beach on Proxima b. This will, of course, affect agriculture. Photosynthesis using chlorophyll works maximally at twin wavelengths of around 470 and 660 nanometers and cuts off to 0 for wavelengths longer than 700 nanometers. So if you take plants from the Earth to Proxima b, they can photosynthesize with only a small fraction of Proxima Centauri's sunlight. But there is a way out to ensure you get fresh food continuously. Silicon solar cells producing electric power have peak conversion efficiency at around 700 nanometers and drop to 0 at 1100 nanometers. So you might be able to carry out farming on Proxima b by placing large solar energy farms, soaking up 700 nanometer light on the hot side of the planet and growing plants in twilight zone greenhouses illuminated by electrically powered LEDs producing the 470 and 660 nanometer wavelengths. So how will the JWST search for life on Proxima b? Well, the first signs of life beyond our solar system might come from extraterrestrial plant life. For example, while the Galileo spacecraft was en route to Jupiter, it pointed its instruments back to Earth and detected the distinct signs of the presence of plants. It discovered what is called the vegetation red edge, or VRE biosignature. This is a mixture of red and infrared light that plants emit. In a similar way, the JWST will measure the VRE of Proxima b. If there is, for example, a jungle on Proxima b, it will give a large VRE signal that should be easy to detect. Apart from plant life, another area the JWST can look at is in the atmosphere of Proxima b for signs of life. When an exoplanet passes across its star, sunlight passes through its atmosphere and could be picked up by the JWST. Spectroscopy would then be used to discover which wavelengths are missing from the light. The atoms and molecules in the atmosphere absorb certain wavelengths, leaving a unique fingerprint for the JWST to detect. In that way, the composition of Proxima b's atmosphere can be determined and the presence of life possibly inferred. If the exoplanet were found to have an atmosphere similar to our home planet, which means it contains mainly oxygen, nitrogen, and carbon dioxide, scientists will conclude it could likely support life forms. But that is not all. Technological life could perhaps be identified by looking for the presence of chemicals that don't occur naturally. If aliens looked at the atmosphere of Earth from a distance, they would probably see chlorofluorocarbons, or CFCs, which were manufactured for use in refrigeration and cleaning materials. Jacob Hack-Mizra at the Blue Marble Space Institute in Seattle has suggested that if the JWST detected CFCs in exoplanet atmospheres, then that would be a telltale indication that a civilization is there. But that is if the life forms on Proxima b resemble those on Earth. If that is not the case, what happens? Well, scientists have some ideas. Even on Earth here, some life forms appear to be alien because of the conditions where they exist. These organisms come under the category of extremophiles. These organisms, mostly microbes, survive in extremely harsh environments where life is impossible for other living creatures. Some live at very high temperatures, up to 250 degrees Fahrenheit. Others bear the extreme cold, as low as -4 Fahrenheit. Some live in strong acids with a pH below 3. Basically, these are places that you would never expect to host life on Earth, but you have these creatures thriving there. The same might be true on Proxima b. Organisms may be surviving in the brutal world of exoplanets, and scientists may even have to come up with new techniques for detecting them. However, it makes sense for scientists to start looking for evidence of Earth-like life, which is why they are concentrating on Proxima b anyway, instead of other exoplanets that have a temperature of 250 degrees Fahrenheit, for instance, or are bathed in acid. And this is why the JWST will first look at an exoplanet system known as TRAPPIST-1, located 40 light-years away from us. It consists of 7 rocky planets like the Earth, and by extension, like Proxima b. All of them are orbiting a cool red dwarf, and 3 of them are in the habitable zone, meaning they could have liquid water in them. The TRAPPIST-1 star is only 1/10 the mass of our Sun and is much cooler, but the planets orbit close to the star, so they receive light levels similar to here on Earth. Let's hear what you think of finding life outside the solar system in the comments section below.